Hello one and all, welcome to the Math Magic Show. In this one, practice finding a piecewise representation for this function, this crazy green graph. In other words, we'll practice how to label each piece, okay? With a function basically, like y equals something or other, and then the corresponding domain that is appropriate for describing that piece. Let's first focus on the piece on the bottom right here. So take a look. When I trace over this piece on the bottom, like this, that basically every y there's -1. And that's true, you gotta look up to the top now. When x goes from -infinity up to -1 itself. So that means I could describe that piece by using this. It says y equals -1 when x is less than -1. Make sure you understand what that says. It means things like this, for example. If I plug in -1 from the x-axis, that wouldn't work here because I said less than 1. But if I plug in -2 as an example, -2 is less than -1 is true. That tells you that the y is equal to -1. You see, that's how you make use of that. Okay, let's look at the next piece. So the slanted piece right here that I'm tracing pretty much. Let me move my camera over this way. Now here, take a look. When -1 goes in, as you can see, -1 comes out along the y-axis. And for example, if -1/2 goes in, -1/2 comes out along the y-axis, and so on. So that's telling you that that's pretty much y equals x. But this one is a little bit different because there's a restriction on the domain, which is it could begin at -1 and go up to 0. The 0 itself, there's like a jump up to 1, so something else has to be put there. So in other words, this first piece, I'm going to describe by saying that it looks like this. Y is equal to x, but this is true only when x has the values between -1 and 0. Notice something important here, that because this includes -1 right here, this one excludes -1. You could also switch it around, theoretically speaking. Wouldn't really make much difference in this case. And now we have to understand what happens at the origin itself. As you can see, there's a hole at the origin, and the value of the function just leaps up to +1 right here. So in other words, I have this single dot where the x-coordinate is 0, but the value of the function is 1. So I would describe it this way. I would say that it's y equals 1 when x equals 0 for this green dot right here. That would describe that one point. Okay. And notice again, because this point is the value of the function when x equals 0 itself, down below here, where I'm kind of located right here, right? That is not included there, because that's included right here at this point, and because it's solid, whereas here it's a hole. Now let's take a look. One last part, couple last parts, like what happens over here for this slanted piece. Again, that's still y equals x, and I know that because, for example, if 1/2 goes in, 1/2 comes out, you see, so the y and x coordinates are equal along the segment. The only difference is there are holes. So for that reason, you see that x equals 0, it's excluded because there's a hole, and then x equals 1, it's also excluded from the domain of the x's that describes this graph portion here, this portion, okay? So I would say that by saying the following now, that y equals x, and this is true between 0 and 1. So what that says, for example, is this. If you want to know the value of the function, you would say, okay, imagine x has the value 1/2. This is the only inequality where that 1/2 would be making the inequality true, because you plug it in there and you have a 0 less than 1/2, and is that less than 1? That is true. And that's telling you then that the y would be equal to that x, which could be, for example, 1/2 or 1/3 or whatever have you, okay? Okay, now the last part might be across this top right here. We gotta handle that one also somehow. So what can we do? Well, you want to always observe, if you look through all of these, the y coordinates, so that's about a 1.5. And then this is true, look down to the x-axis at +1. And I know that because you see this is a solid dot right here. So I might describe this piece by saying the following, that y has the value 1.5 when x is greater than or equal to 1. So again, what that says in practice is, if I want to know the value of the function, and x, for example, has the value 2, then I would plug it in here and I would say is 2 greater than or equal to 1 is true, so the value of the function is 1.5. You can do those kinds of little checks for all of these inequalities. You choose a value of x, you plug it in, you see which inequality is true. It's usually just one of them. Then you look at the y, and that tells you the value of the function. That's all. So for example, one more time. Imagine that x has the value -4. Then you would check this inequality down below here. So is -4 less than -1 is true. That tells you the value of the function is -1. Okay, imagine x has the value -1/3. So you plug it into this inequality, you say is -1 less than or equal to -1/3, and is that less than 0? That is true. that means that the y would be equal to that x. In other words, it would also be equal to negative 1/3. What happens, for example, when you plug in x equals 0? Well, that's true only at the single dot, and you know that the value of the function is 1 again, you see? And so on. That's how you do these kinds of exercises. Okay, that is it for me. Thank you so much for watching. Please leave a like and subscribe. I'll see you in another mathemagical adventure. Hopefully the next one will be less painful.